Dear colleagues and audience, welcome to attend the Professor Andreas Weiermann's last lecture on concrete incompleteness at Wuhan University. Professor Andreas Weiermann got his PhD in mathematics from University of Münster in Germany from 1990. Since 2010, he's a full professor in the School of Mathematics at Ghent University. Since 2018, he's a senior professor in the School of Mathematics at Ghent University. He's a Prof series and make contributions in varied field of logic. Also, he's a leading expert on concrete incompleteness and the phase transition. In the previous 4 lectures, he talked about cut-elimination theorem, Prof theorem of piano arithmetic, Peirce-Harrington theorem, Weiermann's style independence result for ordinal and finite trees. Okay, today is his last lecture. He will talk about the phase transitions. Okay, now let's welcome Professor Andreas Weiermann's last lecture, please.
Recording in progress.
Yeah, thank you very much for this very nice introduction. Today is the last day of my lectures. So if you got interested in the topic of concrete incompleteness, well, there are different sources. You can, of course, look into my papers. It's fine. But most material you will find on another web page, and you could consult the web page of Harvey Friedman. Professor Emeritus at Ohio State University. And on that web page, you will find more than 100 documents related to the topic, in particular a book on Boolean relation theory, and also the recent stuff on tangible incompleteness. And what is spectacular here is not only independence results for arithmetic, but also for strong systems, namely the Miller-Frankel set theory and beyond. Today, we give sort of refinement of the results we have seen before. So I'm studying what I call phase transitions. Now, for my lecture yesterday, I recall some basic material. Namely, we studied the Gaussian sequences at the end. And for this, there's some technical lemma, which is important. It's easily verified by case distinction. And this is so-called Bachmann property. The Bachmann property is responsible for nice properties of the system of fundamental sequences. So if you have the Bachmann property, everything what you need follows by itself. So we define the notion alpha can be reached from beta by stepping down along x.
Oh,
if alpha comes from beta by stepping down almost at the same point x, always at the same point x, but at least one-time application of stepping down. Now this relation, stepping down relation, is stable under addition and also under omega exponentiation. However, with respect to addition, one has to be careful. If one builds sums, then one has to respect certain normal form conditions. But I will not go too much into details. So this I have noted here. So this means that if I write gamma in Cantor-normal form and beta in Cantor-normal form, then the biggest exponent in beta 1 materializes the smallest exponent in gamma. Now, if we have this property, then we have if one can reach alpha from beta along x, and y is bigger than x, then we can reach alpha from beta also in stepping down along y. But in general, one needs more steps from beta stepping down along y to alpha than is needed over here. Okay, and yesterday we made some calculations with Gaussian sequences and to show that the Gaussian sequences are as long as the numbers showing up in the principal H, one has to interleave fundamental sequences with the ordinals associated with the Gaussian process. And this interleaves nicely because one can apply these lemmata about the stepping down relation. Well, that's the moment where we step in today. So what do we prove? We prove independence of principal HF. What is this? For all k, there exists an M such that if I start with omega k, form fundamental sequence at f of 0, then I form to the result fundamental sequence at argument f of 1, and finally I take fundamental sequence at argument f of m. And then the principle states that this is 0. Clearly, for every function f, this is a true statement. What is now the assertion? If f is a fixed iterate of a binary log function or binary length function, then PA does not prove HF. Yeah. Now that's of course not so clear. And for this we need a technical lemma, namely the least I such that if I start with omega k and then I step down at fundamental sequence at argument x, and I do this I many times. This looks like the principle like in H, but here we step down along a constant value x. This is at least as big as we take an omega power of height k, and the base is x. So this is, and basically the upper bound for this is we take this term and replace x by x plus 1, and this term is also serving as an upper bound for this I. Now, how can we prove this? Well, not so easy, but now comes the trick. We consider two new hierarchies. G0 of x is 0. G alpha plus 1 of x is 1 plus G alpha of x. And if I have a limit, G lambda of x is G lambda x of x. Moreover, we define the G0 of x. G0 of x is 0, and G alpha of x is G alpha x plus 1. For the second hierarchy, I add a plus 1 in both situations, and for the capital G, I do add plus 1 only in successor case. In limit stage, I don't add a plus 1. Then one can verify two things. Basically, G alpha of x, what does it do? It has a counter. I step down along the fundamental sequence. For every stepping down, I add a plus 1. So basically, G alpha of x is the least I, such that if I step down from alpha along a fixed x, finally at 0. And it counts the number of steps of stepping down. Moreover, as I said, in the G hierarchy, we don't add the +1 always. So we have G alpha of x is less than equal to G alpha of x. Now, a formal proof requires some calculations, but it's rather plausible that this is true. Now, the last thing which is important is that if I have a Cantor normal form, then this calculates in the following sense. The G replaces in the Cantor normal form omega by x. Now, this is an interesting insight because one can ask, well, what is the relation between our function class capital E and beginning ordinals? And the transition is not done by the Hardy functions, but by the G functions. Now, this is a lemma, which is a nice proof. So therefore, I give the proof. So by induction on alpha, we basically show induction on omega to the alpha plus beta, where beta stands here for the rest. We show G omega alpha plus beta, the same as x to the G alpha of x plus G beta of x. Okay. Case 1. We have beta as a successor, gamma plus 1. Then G omega to the alpha plus gamma plus 1 of x is 1 plus the omega to the alpha plus gamma of x. Just subtracting a 1 here and adding a 1 here. Here comes induction hypothesis. This is 1 plus x to the G alpha of x plus G gamma of x. Now 1 plus G gamma of x is G gamma plus 1 of x. Here we have x to the G alpha of x. So you see the proof goes by itself. Case 2 is beta is equal to 0. Then we are left here with an additive principal number. The first case is alpha is a limit. Now what is G omega to the alpha of x? It is by definition G omega to the alpha of x. Now fundamental sequence for omega to the alpha is omega to the alpha x. So it's G omega to the alpha x of x. Now I can apply induction hypothesis. It's x to the G alpha x of x, and this is x to the G alpha of x. So you see a beautiful calculation. And if alpha is a successor, then what? G omega to the gamma plus 1 of x is G, and then fundamental sequence for omega to the gamma plus 1. So it's omega to the gamma times x of x. Now here's the sum with x many terms for which we can apply induction hypothesis. So it will be what? It will be G omega to the gamma of x times x. This by induction, no, this is yeah. So this ordinal here is smaller than this, so we can apply induction hypothesis. Now G omega to the gamma of x is x to the g gamma of x times x. This is x to the g gamma of x, x to the g gamma plus 1 of x. You see, a very beautiful short calculation. It verifies itself. Now, what is the upshot? The upshot is, why are we doing this? Well, as I said, we want to verify this one. Well, basically, this is G. G omega index k x, which is bigger than G omega k of x. And now we apply this lemma k many times. So this is x to the x to the x k times. So we have this property. Now, but this property is basically explaining why we are able to go along with log star, not log star, but d times iterated of log. Because when we have intervals where there's nothing going to happen, if you have constant intervals, then we see we have here an iterated tower, and the inverse function of such an iterated tower is an iterated log function. And so this observation basically says, how does this cancel out? Okay, now we go into the proof of this one. Well, I modify the starting term a bit, but by making k bigger, one can assume that one has this starting term. So theta is a number. So here I have a deep iteration of binary log. So take we have to know that EA does not prove for all k is an M such that alpha 0, alpha 0, 1, that this statement is unprovable. Now let k be given. Stop. Here's omega k. Now basically, this M is the Hardy function of a level epsilon 0. So assume that we have a sequence stepping down, omega k bigger than alpha 0, bigger than alpha m, and this sequence where m is basically h epsilon 0 of k. Now I have my long descending sequence, but this steps down along the identity function. Now I have to go to a new sequence which steps down somewhat closer, somewhat slower. And for this, I introduce an higher value. So what I'm doing is basically what? Well, I start, let's say, with alpha 0 plus omega d plus 1. So what's going to happen? We have here our sequence. And what we now do is we move the sequence upwards with omega powers. So we form an omega power of high d plus 1 on top. We put basically this. We put basically the first term of this descending sequence. And what is now the assertion? Well, the claim is then there is a number I bigger than h now I have to be careful. If I take this bound here is maybe not completely correct. So if I take here times 2, then I'm fine. Then I have a sequence which is at least as long as epsilon 0 of k. But anyway, if I have a sequence starting from alpha 0 along the identity sequence, then I get here a new sequence. The new sequence is I take beta from f of 0, f of 1, f of I, at least as big as omega d plus 1 of 0. Important is that this number is not 0. So this means I can find a descent starting with the large beta using the stepping down, this slowed down, stepping down along function f. So if this lemma is shown, or if this property is shown, then basically you see that we are done. We have found a fixed alpha, fixed beta, such that stepping down along beta takes a long time, unprovably long time. And now stepping down, let's say this is beta, having this form. So here we have omega d plus 1 applied to omega index to k. But now if we go to a much higher power, let's say omega to the d plus 4k or so, then we can step along from this bigger ordinal to this ordinal beta using the properties of the fundamental sequences over there. So without loss of generality, we assume that this is sufficient to show the assertion. Now, what we are doing is let's watch. Well, we make also certain assumptions. So f is iterated log function, but for simplicity, we assume that f starts somewhere. It's the maximum taken over 2 and this number. But this is purely technical. It's not that important. But just adjust the starting values a bit. Okay, here is this number, beta. Omega d plus 1 alpha 0 plus omega d plus 1. And now I step down along number 2. So that's the reason why I assume that I have here at least the maximum given by 2. Otherwise, I have to do some padding operations such that I wait long enough such that the function f becomes at least as big as 2, but I forget about these minor issues. So the next step, we get here omega d plus 1 alpha 0 plus omega d plus 1 of 2. Then we step down again along 2. And now you see what's going to happen. We just step down along number 2. So this takes a certain number of steps. Call it I1 many steps. Stepping down along 2. Finally, we will hit here 0. So we will get omega d plus 1 of alpha 0 plus 0 and so many steps. The number of steps I1 is bigger than. For this, I needed this technical lemma from here. Namely, I get here an exponential by 2 by e plus 1. Now, what we see is when we step only down along 2, that's fine. But now this number 2 is less than or equal to all the values of function f of I, because it's a maximum of 2 and this binary log. Now, if we look at binary log d times iterated applied to I1, then we see suddenly some number shows up, namely what? Number 2. Maybe that's not so good. I want to have a bigger number, maybe 4. So nobody will complain if I just move d plus 1 into d plus 2. Making these numbers bigger means that the sequence becomes longer. Okay, but now this function f applied to this number is at least as big as 4, bigger than 3. But maybe we take 4, that's fine. Because now when we do the stepping, we step down along 2. Now we can replace every 2 by a function value of f using this property over here. So we replace all these numbers 2 by f of 0, f of 1, etc. Here we replace these 2 by f of I1, which is 4. So this means from beta, stepping down along f, I1, omega d plus 2, alpha 0. The last step will be given by number 4. Now, what's going to happen is we step down in the fundamental sequence for number 3. So here we can step down along fundamental sequence at argument 4. And if you step from argument 4 down to number 3, I can guarantee that I can get here a remainder term omega d plus 2. Well, this is a technical calculation. I will not bother you too much with these technical calculations, but this is the point. So I first step down to, here's a 4. This will be at least as big as omega d plus 2 alpha 0. Now 4 will be replaced by a smaller number 3 plus omega h plus 1. And why is this the case? This case because we know that alpha 0, 4 is bigger than alpha 0, 3. With respect to 1. And therefore, it is bigger than this number plus 1. So, what does this mean? This means that in this situation, I can replace, so this is basically what's going to happen. So this is alpha 0, 3 plus 1. And now here's a plus 1 high in the exponent. And if I step down along 4, I finally end up with omega d plus 2, alpha 0, 3. And this plus 1 translates finally, after many steps, to omega d plus 2. Now, what one can do is one can replace this argument step by step. The next step is, well, we take this number, and here we step down along 2. Now we take this number and step down along 3. We obtain omega d plus 2, alpha 0, 3, plus omega d plus 2 of 3. And then we continue until we hit, so here we just step down along 3, omega d plus 2, alpha 0, 3, 3, 3. This needs, this was I1, this needs I2 many steps. Oh, stop. It's not correct. I was a bit too quick. So I'm doing stepping down in this now. So here's alpha 0, 3 plus omega d plus 2, 3, 3, 3. And this happens I2 many times until I hit 0. Now the number I2 is bigger than 3 to the 3 to the 3 of pi d plus 2. So this means f of I2 will be bigger than 3 to the 3. And now you see basically what's going on. We build this sum, then we kill the last term by stepping down along a fixed number, and we can replace a fixed number by values of the f function. And every now and then, the f function starts growing. It jumps function value from number k to k plus 1. And this happens after a long time. But the time that this is going to happen has to do with building up high enough powers. Now, this procedure is basically set up in a way that you can replace this stepping down procedure by using this property. So first we step down along a constant function. Then we replace the stepping down by the f function, which means that we take even longer. Then we hit the first number, which is here. Then we step down with the function value which we obtained over here, which is bigger than the stepping, or 2 bigger than the stepping down before. Then we do one step with respect to this new bigger number. We replace this bigger number by -1. So 4 is replaced by 3. But we add here +1. Using the property that alpha 4 is at least as big as alpha 3 plus 1. In case that alpha is a limit. And if alpha is a successor, you can just jump directly to this number. Then we build fundamental sequence. We cut down this number. We add here a new omega d plus 2. And then we work again on this one. And once we have worked on this one, stepping down a fixed fundamental sequence, but now with bigger index, we wait how much time is needed. It will be an iterated exponential with a bigger base, so that the iterated log function gives here a bigger value. And then we repeat this procedure. And now, to summarize the argument, this is basically it's a bit difficult to explain. So what is the idea? The idea is we have here a sequence alpha 0 bigger than alpha m, stepping down the identity function. Now I make here sufficiently high power of alpha 0 plus some extra stuff, which is rather small. And this steps down to omega d plus 2 alpha 0. Then we do a step in the fundamental sequence for alpha 0. We get here basically alpha 2 plus omega d plus 2. Then we kill this term. We obtain omega d plus 2, alpha 0 of 2. Important is that the number of steps to kill this term is so long that after having worked out all these stepping downs, the value of the function f increases by 1. So this means after having carried out this, the index in stepping down becomes big enough that we can jump to the next number, so form alpha 2, 3 plus omega d plus 2. And now we kill this number, but now with a bigger index. We wait when this is going to happen. And log d applied to the number of steps are needed will again jump by 1. And so we will end up here with a form number of the form alpha 0, 2, 3, 4, etc. So what's going to happen? We have a descending sequence of ordinals. And what we do is we do some padding, namely from this sequence, we make a new sequence. The important point here is we move this ordinal upwards by a fixed height of omega powers. And the fixed height of omega powers basically explains that I have enough space for stepping down for constant time in the meantime. That this compensates for the function f, such that when I worked out this number of steps going down, that the index here is always added by a 1. And so the original sequence shows up in the sequence which we have here. The sequence we have here is obtained by stepping down along the f function. Well, this should suffice as an argument. Maybe a bit messy, but one can make this fully precise and then it works out. Now, the next result is the following. Namely, if f of I is binary log of I, and now I make the D dynamic, I plug in here H epsilon 0 inverse of I. Now, what is the inverse of a function? If f is increasing, unbounded, then f inverse of m is the least n, such that f of n is as big as m. Now, h epsilon 0 is a fast-growing function. H epsilon 0 inverse is a very slow-growing function. And now these functions grow even slower than those functions. Here's a fixed number d, and here's a dynamic number d, which becomes bigger and bigger. Still, PA does not prove HF. Now, how to think about this? Well, the point is, from the viewpoint of arithmetic or the formal system Z, well, H epsilon 0 is not provably total. So one cannot prove that in this system that the H epsilon 0 inverse function is unbounded. So it could be that in some standard model, this number is bounded. And for bounded number of iterations of logs, we have an independence result. This intuition can be made hard. So in the following sense, namely, the lemma is if alpha is a specific form, namely omega d plus 2 of omega index d, or maybe I put here k, plus omega k plus 2, then the least I such that I take alpha Now f of 0, f of 0, f of 1, until f of I. This is, it's 0 is bigger than h omega k of 1. Now the function k goes to h omega k of 1 is not provably total, because this function comes basically from this principle where f is identity. So this function here, these function values produce rather large numbers, unprovably large numbers. And now if I take k as an argument, I don't start with omega k, but I move it upwards to omega k plus 2 of omega k plus omega k plus 2. Then I get a sequence which is as long as this number. Now this is magical, because how is it possible to deal with the h epsilon 0 inverse function? Well, for I less than equal to f h omega k of 1, we have. And now comes a very crucial idea. Namely, we want to control the inverse values of h epsilon 0. Right? H epsilon 0 inverse of I is less than equal to, well, h epsilon 0 inverse is weakly increasing. So we can plug in this number. This is bounded by h epsilon 0 inverse of h omega k of k, maybe k plus 1, doesn't matter, which is h epsilon 0 inverse of h epsilon 0 of k, which is equal to k. So this is a trivial observation, but this is important, because this means I take binary log I h epsilon 0 inverse of I many times iterated. This number is bounded by k, so smaller number of iterations. Smaller number of iterations means that this is bigger than larger number of iterations. Now we apply basically the lemma which I just wiped out. So we reach zero from alpha, from this alpha. Yeah, how many steps are needed? need at least h omega k of 1 many steps. We reach 0 from alpha and at least h omega k many steps if we step down along the function I goes to log k of I. So k is fixed, and for the fixed iterates of logs, I've just given a lower bound for the number of steps. Now these numbers are bigger than those numbers for I less than equal to h omega k of 1. So we have here alpha, and we can step down. And here we use for this function fk. So here we step down function fk. Now the number of steps here is at least so big. Now if we zoom in to h omega k of 1, then we know if we step down from alpha in h omega k 1 many steps, we do not yet hit 0. Now we look at this interval, and on this interval we apply this observation. On this interval we have this inequality. So if I is not too big, if I is bounded by h omega k of 1, and I can replace this stepping down by stepping down along f. I also do not get 0. And this means that stepping down from alpha to 0 needs at least omega hk1 many steps. Now, what is the trick? The trick with this argument? The trick with this argument is the following, namely, we have this inequality. But this inequality does not hold for all I, because h epsilon 0 inverse of I finally goes to infinity. So at some moment, this number will be bigger than k. But the important point is, in the beginning, when we are not too far, it's a reverse inequality. And we only need the inequality for the beginning to import the result for constant d to dynamic d. That is basically what's going on. So in the beginning, the asymptotics does not apply. So we can apply the lemma for fixed d using the other lemma, and then we are done. That's the magic. So the magic is this easy observation, which leads to this inequality for an initial interval where stepping down along a fixed fundamental fixed fk is at least as long this k is shorter than the stepping down along f, where f is working with this dynamic d. Okay, that is basically the treatment of this principle H. Now we come to the next topic, which is Kruskal's theorem. and I wipe out the board. Well, I think it's better first to treat the slowly well-orderedness because it's easier, and then I do cross this theorem. So the slowly well-orderedness was the following principle. Slowly well-orderedness with respect to F is the following principle. For every K, there's an M, such that for all alpha 0 to alpha M, if for all I less than equal to M, we have that the norm of alpha I is bounded by K plus F of I. Then there exists an I less than M such that alpha I is less than equal to alpha I plus 1. And what do I want to prove? I want to prove that, or PA, does not prove SWO of F, where F of I is log of I times a fixed iterate log D of I. And how can I do this? We have seen last time if we have this principle SWO prime, where one has here K times 2 to the I square, then it is unprovable. Now this goes in steps. So step 1 is assume, so we show what? Lemma. So SWO for the identity implies SWO for this function F. No, that is other way around. SWOF implies SWO identity. So what is the implication? I want to show that this is independent. Assume that this is provable, then this is provable. This is unprovable by Harvey-Friedman's result. So this is a good start for our calculation. So how to prove this? Well, and basically, what is the idea? The idea is consider, let K be given. Now, I want to show that this is unprovable. I assume that this is unprovable. Let M be minimal according to SWOF identity. And then consider M minus 1. Well, I want to show that this principle SWOF is independent, assuming that SW identity is independent. So the idea is I take K, and then I choose, according to SWO it, the minimal M, but this is going to hold. So M as function of K is unprovably large. This also means that M minus 1 is unprovably large. Now, if I take this M and subtract the 1, this means I'm able to find a sequence alpha 0 bigger than alpha M minus 1, such that the norm of alpha I is bounded by K plus I. And now I find a new sequence, alpha I prime, which is as long as M, which fulfills basically the norm condition. Norm alpha I prime is bounded by K plus F of I for this F. So I take a long descending sequence for the identity, and I move it into a long descending sequence for the new function F, where I can assume that I'm allowed to make the K a bit bigger for the new state. Okay. How does this work? Well, let what? The norm of alpha 0 is less than or equal to K. So what does this mean? This means alpha 0 is smaller than omega index K. So if we have an ordinal which has norm smaller than bounded by K, then well, the norm of omega powers, norm of omega K is K plus 1, so that's fine. Let what? Alpha I prime. Now comes the trick. We do what? We have here number D. So we do the same as in the Goodstein principle. We take here number D. And maybe for simplicity, we make it a bit bigger. So for whatever reason. Then we take alpha. This is alpha I prime. And instead of alpha I, we take here the binary length of I. Well, I write here binary log of I, but this is rounded along the binary length function plus something. And then we take the enumeration function, the set mi, and argument 2 to the binary length of I minus I. So here is binary length. Now the question is, what is mi? Mi is the set of all ordinals beta smaller than omega d plus 2, such that the norm of beta is less than equal to log I times log, here I take d plus 1 of I. Now what? Mi is a set of ordinals bounded by omega d plus 2, such that the complexity norm beta is bounded by this function. And then here comes the enumeration function. This enumerates the elements in increasing order. So the enumeration function at argument 0 takes the minimum, then at argument 1 I take the next one. But what's going to happen here is basically I want to enumerate the elements of Mi in decreasing order. So I take 2 to the binary length of I minus I. And then it basically goes in the other direction. So first comes bigger ordinals and then come the smaller ordinals. Now what's going to happen? Well, then alpha I plus 1 prime is smaller than alpha I prime. Why is this the case? And as I said, this construction is set up in a way that I'm enumerating the elements Mi in a decreasing order. That's good. So from a descending sequence of ordinals alpha I make a new decreasing sequence of ordinals alpha I prime. What can I say about the complexity? Now this is important. Here we see basically a new technique. The norm of alpha I prime is bounded by d plus 2 plus the norm of alpha binary length of I plus, I don't know what the norm here is, but is bounded by this term. So it's bounded by binary length of I times binary length iterated d plus 1 many times by 2i. This is bounded by d plus 2 plus, now here comes the trick. So the norm of the norm of alpha I is bounded by k plus I. So this is bounded by k plus, and here comes binary length of I plus log binary length of I times binary length d plus 1 times iterated applied to I. And here you see this is bounded by, now by making k a bit bigger, I can here assume the asymptotics binary log of I times, and now I make this number bigger, log d I. So what has happened? The important point is happening here. From alpha I go to alpha index binary log of I. This means that those ordinals are having lower complexity. They're just complexity k plus binary log of I. So I get here a term, but since this is slowed down, the overall complexity is as we would like to have, namely this function. That's great. So from a given descending sequence, I make a new descending sequence, which in complexity grows slower. There's only one issue. The issue is I enumerate the set, but for this I need that this set mi has enough elements. The enumeration function has to be defined. I need here basically 2 to the binary length of I many elements. So finally, alpha I prime is well defined because the cardinality of mi is bigger than 2 to the. One has to be a bit careful. Is binary log, but what I mean is the binary length of I, which is a bit bigger, is basically this function. But for the viewpoint of the presentation, it does not matter too much. So what I'm assuming here is really the binary length function, which is defined by this term. So overall, where there is binary log here, I replace binary log by binary length function. But you know, the distance, difference is minimal. Well, now the problem is that this is a non-trivial issue. Because if mi would always have enough elements, then I could squeeze down the complexity as low as possible. Now for this, now comes combinatorics. And we need the following function. C beta of n is counting the number of basically alpha less than beta, such that the norm of alpha is equal to n. Now the question is, what is this function? And it's known, theorem, the omega to the omega of n is asymptotically, one would expect an exponential function, but it's not the case. A sub-exponential function. So it has a form e to the pi square root of 2 over 3 times n divided by 4 times square root of 3 times n. So you would not guess this when you would just see this function. But for this, you can just apply a classical result in number theory by Hardy and Ramanujan. And actually, this number is the nth partition number. And when you see partition numbers, then you find this easily. And what one can also show is if one has omega power of height d plus 2, and takes the natural log of this. This is basically pi square over 6, n divided by, and here we have a d times iterated binary log function. So here's binary log function, d times iterated, where d is at least as big as 1. So suddenly you need some external information, which I will not prove. This requires generating functions and a bit of analysis. Well, for those who want to see a bit more details, the argument is basically that I have C omega to the omega n, and I form the generating function, can be written as follows. You get basically such an infinite product. And then by magic, using some tricks with Cauchy's integral formula and some estimates, you can get this result from this representation. And in general, when you want to have results on omega powers, I think when I remember correctly, it has the following form. And here I have, I think, C alpha I, that don't know, either +1 or -1, maybe +1. But the point is, by having asymptotics for C alpha, I can generate asymptotics for C omega to the alpha. But this would require lots of time, so I will not do so. But now let me finish this presentation by showing that this is true. So what can we say about the number of elements in MI? This is at least as big as, well, what is MI? Oh, MI has disappeared. MI was a set of all beta less than omega d plus 2, such that the norm of beta was bounded by binary length of I times E times iterated binary length of I. So this number is at least as big as what? We take into account, well, here's with log, so it's basically 2 times exponent is a constant. And then we have this number here. So we have here log of I times E times iterated by log of I divided by, we have here d plus 2 d plus 2, then you have here log d of, and then comes log 2 of I times log d of I. And then you basically see by magic, it's not so good. So I want to have that this number is bigger than to the binary length of I. And yes, that's true, right? Here is log d of I, one more log. So this one divided by this one is bigger than 1. So we get this one. So by magic, the result comes out. What we learn from this is the threshold function, this one here, comes as basically as inverse function of the counting function for the ordinals involved. And yeah, this is basically the argument. Now I was a bit quick. So I was writing alpha I prime was omega d plus 2 of alpha binary lengths of I plus enumeration of m of I in inverse order. And then I said that if alpha I is a decreasing sequence, that alpha I prime is a decreasing sequence. Now, why is this the case? Assume that I is bigger than J. I want to show alpha I prime is bigger than alpha J prime. There are two cases. One case is if the binary length of I is bigger than the binary length of J, then this ordinal, alpha binary length of I, is bigger than alpha binary length of J. Now I made this ordinal big enough with an omega power of I d plus 2. So if this ordinal is bigger than the corresponding ordinal with the J, well, this what I add over here, the elements in Mi are smaller than omega d plus 2. So once an ordinal here is big enough, here this means alpha binary log of I is bigger than alpha binary log of J. And if I have here that this number is bigger than the corresponding number with J, what I'm adding here doesn't matter because it's smaller than omega d plus 2. The other case is, if this is the case, then I have alpha I prime bigger than alpha J prime. And if the binary length of I is the same as the binary length of J, then basically these two numbers, log 2I and log 2I times log d of I is equal to log 2J times log d to J. And then I'm subtracting in the number in the set Mi, which is equal to Mj. Well, then I'm going down in a decreasing order. Then the stepping down from alpha I prime to alpha J is caused because I have here strict decrease. Okay, so this is a treatment of slowly well-orderedness. And now I see I'm already using much of your patience. So after the break, I want to cover still two theorems. One is Harris-Harrington, and the other is Kruskal's theorem. But now there's a 5 minutes break.
Recording stopped.
Okay.
Recording in progress.
Okay, we can start again. So in the break, there was some question about the organization of the argument. It was maybe not completely clear. So the idea was to show that SWF implies SWO of the identity. Now, then I started with given K, an unprovably long sequence for this principle, and then I produced a long sequence for this principle, but this was not maybe precisely showing this implication. So let us reformulate the idea. So let K be given. Now consider K prime, which is an easy function of K, let's say number D plus K times K, something like this. So a simple polynomial in K, big enough for our purposes. Then choose M according to SWOF for this K, and show this is good for SWO identity. This K prime and K. So this M is good for given K for the principle SWO it. Now, how do we prove this? So let sequence alpha 0 to alpha M be given such that the norm of alpha I bounded by K plus I. Now build as before alpha I prime. Then, by the calculations we did before, the norm of alpha I prime bounded by K prime plus F of I. So in K prime, I hide the information that we have coded some D and whatsoever. But anyway, now by SWOF, there is I smaller than M, such that alpha I prime is less than equal to alpha I prime alpha plus 1 prime. Okay, now there are two cases. The length of alpha I is the length of alpha I prime. The binary length I is equal to the binary length of I prime, I plus 1. But then we look into the definition of alpha I prime and alpha, and we look into the definition of alpha I prime and alpha I plus 1 prime. And if the binary lengths are the same, then we have a descent regarding to the enumeration function mi. So this is impossible. Hence, the binary log of I is at the critical moment bigger, smaller than the binary lengths of I plus 1. And then we can conclude that alpha binary log I plus 1 is log alpha I is less than the corresponding number alpha log prime I plus 1. Because we have this property, and then we have the corresponding property for the ordinals in this representation. So alpha I prime was omega d plus 2 of alpha binary log of I plus enumeration stuff. And if we would have here that this number is bigger than this number, then this would not be the case. Therefore, this is less than or equal to 2. And then we have found indices, this number is smaller than this number, such that alpha index, the first number, is smaller than the second number. And then the sequence of the alpha i's is not strictly decreasing, and therefore we are done. Okay. Now, we are not fully done yet, because here is F, here is identity. Now we have to prove implications from SWO identity to SWO of, let's say, what? Well, we can take here an exponential function, and here, let's say, two to the maybe square root of I. Anyway, it doesn't matter that much. So from a lower function, we can go to a slightly bigger function. And the idea is we iterate the proof, which shows that from the small function f, we can go to the identity. Then we move the identity to a stronger function, let's say a sub-exponential function, which goes faster than every polynomial. And the proof goes by copying and paste. Just we have to modify the corresponding estimates for the norms. But this logarithmic compression technique proves something like this. And then we show from SWO to the root of I, we get SWO 2 to the fourth root of I. Again, by applying this technique. What was the idea? The technique is basically from a sequence alpha I, we go to a sequence alpha log of I. And if you apply the log function to this function here, then we get a function which is slower than this function. And if you apply log function here, you obtain a function which is slower than function here. Finally, we built up here a specific tower. I think this tower is already fine. And now we have to deal with the function k times 2 to the I square, I plus 1 square, which we have seen yesterday as bounding function for the principal SWO prime. But now this function, so let's say k square plus 2 to the I 1/4 is bigger than k times 2 to the I plus 1 square, at least for I big enough. And then we make an easy conclusion that the SWO principle for this function follows from SWO of this function. So this finally shows that this principle is independent of Bernoulli. So we slowly move our threshold to bigger and bigger function until we hit a number which comes from the provably total functions. Okay. Now we do the same for Ruskell's theorem, FKT. What was this? For k, there is an m such that for all sequences of finite trees, if all I less than equal to m, we have that's the number of points in number of nodes in Ti is bounded by k plus f of I. Then there's I less than j, such that Ti is embeddable into Tj. And the final result is the following. Assume what? Tn is the number of trees T, such that T has basically n nodes. This is totally equal to alpha to the n, n3 over 2 times a constant, where alpha is basically 2.95776 or something like this. There's an explicit description of alpha, namely alpha comes as follows. Let T of z be a power series, sum over Tn z to the n, the generating function, and assume that this has a functional equation of the form z times exponential, complex exponential of ez to the I divided by I. Then let rho be the radius of convergence of T. Then alpha is 1 over rho. Now the question is whether this helps us further. But it's possible from this type of material to give estimates for these numbers, the decimal expansion. Anyway, we forget about this stuff from analysis. We just need this bound here. For this specific number alpha. Now the result is theorem let fr of I be equal to r times binary log of I or binary length of I, it doesn't matter. If r and c, the constant is 1 divided by now really binary log of I, binary log of alpha, so it's not rounded, just the real number. If r is less than equal to c, then a or z proves fkt fr. And second, if r is bigger than c, then pa does not prove fkt fr. And now we are going to prove this. And actually, the proof is S for the principle SWO. And I give a sort of similar proof. And I follow my exposition, so not to be confused with the notation. So what do I assume? We assume that PA does not prove FKT for F index 4. That's the theorem by by Matusek and Löbel. Now, this is an assumption, but we will see we can get rid of this assumption. Now, what we want to show is, assume that this is unprovable, then for R bigger than C, FKT FR is unprovable. So proof of version 2. Okay, now we do the same strategy as before. Assume K is given. And now let M be as in FKT F4. So this is an upper bound M such that all sequences which fulfill the norm condition for F4 are not bad sequences. So there's the numbers I and j such that Ti is embeddable into Tj. Consider M minus 1. M as a function of K is big. M as a function of K is unprovably large. Now, if we have M minus 1, then we find sequence of trees E0 to EM minus 1 such that there are no indices I and j such that I is less than j and Ti is embeddable into Tj. And the number of nodes in Ti is bounded by K plus 4 times binary log of I. So we have a counterexample, so to say, for F4, and now we make a long sequence counterexample for FKT FR. So what we are going to do is we show that we can move the sequence of trees Ti into a new sequence of trees T prime I, such that this property holds for Ti prime, and such that we can replace here the 4 by number R. And for this, we can make the K a bit bigger, but this is not so important. Okay. So we have R is bigger than 1 divided by log 2 of alpha. Now comes another thing which we have to assume, namely we have to study this number, we have to study numbers T and D, which is a number of trees T, such that T has n nodes, and the out degree of T is bounded by D. What does this mean? Well, when you have a tree, and in a tree there's a node, then there are at most D many direct successors. So the number of, there's a branch, a bound on the branching of the trees. T and TDN comes with an asymptotic alpha D to the n divided by n 3 over 2 times another constant. And what we need is that alpha D as a function on D converges to alpha. Now, proving this would require 2 double hours. So there's an article in the literature by Go and Schmutz in Random Structures and Algorithms. And they show this. They show even a result about the speed of convergence of alpha D against alpha, which is a very refined result. But we just assume that alpha D converges to alpha. Okay, now we have R is bigger than this. Choose some number R prime. R bigger than R prime, bigger than 1 divided by log 2 of alpha. Now alpha D converges to alpha. So for D large enough, we have that R prime is bigger than 1 divided by logarithm with respect to base 2 of alpha D. Now what? Well, we are now going to define the TI primes. The modification, so moving those trees into new trees. And there are 2 things to consider. First, we start with T0, and then we do some sort of preparatory step, namely, as we did for Paris-Harrington, that we chosen some number, we added a big number, and then we subtracted a 1. I will not carry out this type of padding. I will just assume I is big enough to explain the essence of the construction. So what's going to happen? We take 3 Ti, but not Ti, but here comes the binary log of I. We take bar to denote binary log. This is a tree. Then I go 1 node below, and I make up a new tree here with E plus 1 many direct successors. I go further down. And here comes specific tree. And I write it down. Enumeration of mi, 2 to the binary length of I. Minus I. I have to say what is mi. Mi consists of the trees T, such that the out degree of T is bounded by D. Now you see the role of D comes here. Here is D plus 1. Here the out degree is bounded by D. The number of nodes T is bounded by R prime times binary log of I. We have seen something like this before, namely by the treatment of SWO. We have the old trees, then we do a logarithmic compression in the index. So Ti is replaced by T binary log of I. Then we do something with this. And here comes some filling up stuff according to a set of trees which fulfills this bounding condition. Now, that's fine. Now comes observation, namely, what is the number of nodes in Ti prime? So it's bounded by K plus. Now we assume here the bounds here, 4 times log of binary length of I. Double log. Plus R prime times binary log of I. Now you see R prime is smaller than R, so this is bounded by some K prime plus R times binary log of I. So from the given sequence here, which is bad, fulfilling this property, I obtain a new sequence Ti prime, fulfilling the property that number of nodes in Ti prime is bounded by the function is R times binary log of I as expected. And to make this asymptotics work, we have to make this K a bit bigger than before. Now I was a bit cheating. I forgot about this part here. So we get some monos, 1, 2. So here comes another plus D plus 3. But since R prime is smaller than R, K plus D plus 3 plus 4 times, and here is log of I, which is smaller than log of I. So all of this, what is here, is bounded by this term. Okay, that's good. Now the claim is there do not exist I and J such that Ti prime is embeddable into Tj prime. Why is this the case? For this, we need our specific construction, namely what can happen. Well, I I will proceed slowly. So here we have T I prime, which is here T binary log of I. Then we have here a tree of branching T plus 1. And here is enumeration function of mi, who to the binary length of I minus I. Here comes Tj prime, which is T binary log of j. Then comes the same tree. And here comes enumeration function of mj, who to the binary length of j minus j. Okay, now assume for contradiction that this is going to hold. Of course, this can happen. Now, first of all, is it possible that Ti prime is embeddable into this right direct subtree? The answer is no, because in enumerating these sets here, I assume that I only enumerate trees where the bounding degree is bounded by D. If I move the whole tree into this small tree, I have to move in a tree where the out degree is, there's one node with out degree D plus 1. And this homomorphic embeddability relation respects the out degree. So if I move the whole tree into this one, then I need here in this tree a point which has out degree bigger than D. So this is impossible. It's not possible to move this tree into this tree. Is it possible to move this tree into this tree over here? Well, this is also not possible, because then this tree has to be moved into this tree. Now, the binary log of I is less than or equal to the binary log of j. If this tree is embeddable into this tree, then these trees are the same. But then it's impossible to move the whole tree into this tree, because this tree has more nodes than this immediate subtree. So it's impossible to move the whole tree into this subtree. Therefore, the root has to go into the root over here. Now, we have to figure out what is possible. So this tree, if the root goes here, then the immediate subtrees here have to go into immediate subtrees over here. This immediate subtree here cannot go into the right-hand side due to reasons of out degree. So this tree has to go into this tree. This is only possible when this tree is embeddable into this tree, and then these three have to be the same. So binary log of I has to be binary log of j. Okay, and then this tree has to be embedded into this. Now, I have not fully explained what I mean by enumeration function. So here I have tree T. I have to figure out what is enumeration of mi. So mi is linearly ordered by an extension less than equal to plus, which extends the tree embeddability relation. So every partial order can be extended to linear order on finite sets. Then the enumeration function is well defined, enumerating trees in increasing order. But then a later tree would be embeddable into a previous tree, which is impossible by this condition on this linear extension. So this is also not possible. So in total, we get the situation that this leads to a contradiction. Finally, we have to check that MI has enough many elements. The number of elements in MI has to be at least as big as 2 to the binary log of I. Why is this the case? Well, for this, we need our complexity bound, namely MI fulfills this property. The number of elements in MI is at least as big as, now comes alpha D, to this complexity bound, K prime plus R times binary log of I, divided by K prime plus R times binary log of I to the 3/2 times the constant. And I have to show that this is at least as big as 2 to the binary length of I. Why is this the case? It's not so clear yet. So let's bring this to the other side. Comes some stuff. K prime plus R times binary log of I. Well, now the crucial element is that here is not alpha, but alpha D. So this is 2 binary log of alpha D. Let's see. Yeah, what is R? R is 1 divided by binary log of alpha. I think yeah. The point is here's R prime. So here's R prime. So MI consists of 3 T's, 3 is T, out degree is bounded by D, and the number of nodes is bounded by R prime times binary log. Now R prime is bigger than this number. So log 2 of alpha d times r prime is bigger than 1. So this number times r prime is bigger than 1, and when I becomes big enough, this is a reasonable estimate. Okay, now you ask, this works for large enough I, and this can be made the mathematical argument by defining ti prime for large enough I in this way. And if I is too small, I do some padding arguments. This is not so important. But the crucial argument is hidden over here. So I fix my number r, I go to r prime. Then I choose d, such that this holds. And then finally, I find enough trees so that I can define my trees ti prime. And so from a bad sequence for 4 times binary log, I can make a bad sequence, long bad sequence for r times binary log. Now this proof shows how I can move from SWO F4 unprovable implies SWO FR is unprovable. Now the next step is we take Friedman's statement for linear functions. If you have here the identity function, we can make the same argument. Now here we just plug in place of r times binary log, 4 times binary log. And then we apply the technique to the identity function. If this is unprovable, then SWO F4 is unprovable. This leads to an independence proof of the Matuszek-Löwe result, knowing the Friedman result. But this logarithmic compression technique works like this. But SWO is not the right one. It was FKT. Yeah, maybe I use this here. So recap from FKT F4 unprovable. I can derive FKT FR is unprovable. From FKT identity unprovable, can derive FKT F4 is unprovable. If I have FKT 2 square root of I unprovable, I can prove FKT identity unprovable. And from FKT 2 to the I 1 over 4, I can prove FKT 2 to the square root of I. Finally, this is unprovable. FKT 2 to the I to the 1 over 4 is unprovable, since we have seen FKT, and then let's see the function FKT for k times 2 to the I plus 1 square is unprovable. That we have seen yesterday. So to squeeze out unprovable statements, you have to apply this logarithmic compression technique several times, and every step you squeeze down your threshold by some sort of logarithm, down, 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 and then finally you get the result. Now, what is the big picture? And then I conclude for today. The picture is this one. We have one region for fast-growing function. We have here unprovability. For the red function, we have unprovability. Now we make this function slower by applying logarithmic compression. We get unprovability for function of lower speed. Then we do this again. And again. Finally, we will reach a point where we cannot do again get further compression. And what is the argument? Well, the point is we always had to use the functions mi with these bounds. Right, no, disappeared. But the number of nodes in T was bounded by a certain function. And we have to guarantee that the sets mi contain enough many elements. And we reach finally the level of the threshold function, the final threshold function, at a moment where additional compression is no longer possible. And that's the final upshot, the threshold function. And then what is left is to prove the provable version, but that's a simple counting argument. If you have the function fr, fkt, fr for r less than or equal to c. And that's an easy student exercise to see if you have a sequence of trees such that the ice tree is bound, the number of nodes in the ice tree is bounded by such r times binary log, that those sequences cannot, they are always bounded by a double exponential function. Therefore, probably this is provable in Peano arithmetic. Okay, and now I see I'm a bit over time, but I wanted to conclude this. I was not able to cover the Paris-Harrington theorem, maybe next time. Okay, thank you very much. Yeah.
Okay, a very brief conclusion since this is the last lecture. First of all, we thank Professor Andreas Weiermann give all very wonderful 5 lectures. These 5 lectures are closely related. Also, his lectures give us a unified general way for proving concrete incompleteness. It works very hard. Most lectures are over 2 hours. Secondly, we also thank for all online on-site participants. And finally, we thank the online and on-site managers. Okay, that's all for the Professor Andreas Weiermann's lecture. Okay, thank you.
Yeah, and at the end, thank you very much. Let me also say, 1 week or 2 weeks ago, I gave a presentation in Beijing. It's this ICBS conference. And that talk will also be put on the internet. So if you are interested in more results on phase transitions, you can also have a look over there. But that is just a talk with mentioning the results without giving any proof, just with a trivial proof. And that talk, I was mentioning this event and was just claiming that in this course, I will provide the details for the announcements which I gave in the talk in Beijing. Anyway, thank you very much for your attention, and I hope that you enjoyed this. And today I did not bring in my paintings because they are already in my suitcase, and today I'm flying back to Europe. But yeah, you can find paintings of mine, if you're interested, even on the internet. Just Google and use some search machine, you could find some. Okay, thank you very much.
Recording stopped.